Oh, can you hear me now? Yeah, okay. Won't speak too loud. Good afternoon. My name is Michael Sadler, and I am the Technical Director with Next Lubricants. So the topic of the presentation today is natural refrigerant gases and their effect on lubricant properties. So what does a lubricant do? So the key aspect is a lubricant lubricates. Lubricant is also designed to provide seals, to protect against corrosion, to reduce heat. And of course, for a refrigeration lubricant, we also have to have either good miscibility or we have to have immiscibility with the refrigerant. Of course, it depends on the system itself. So before we really get into this, I think it's important to have a discussion over the differences between miscibility and solubility. This is a topic that is often confused. So miscibility is the ability of the refrigerant to completely mix with a lubricant. And really, depending on the type of refrigerant and lubricant mixture, there's often a maximum of concentration of refrigerant that can be absorbed into the lubricant. Solubility is the extent to which a refrigerant can dissolve in a lubricant. And in a refrigeration lubricant, solubility is referenced when we're determining what kind of effect that refrigerant has on the lubricant itself. So again, miscibility is dependent on temperature and within a miscible region. So right here, this is an example for POE with CO2. We can see that there is a very large miscible region. So this is a region where the lubricant and refrigerant will be completely mixed with each other. Outside of this region, you can see a small region. This is where we'll have immiscibility, where there will be a separate layer between the refrigerant and the lubricant. So there are, in general, two types of systems. So in ammonia refrigeration, we want to see immiscibility. We do not want the refrigerant and the lubricant to mix as much as possible. This is because in immiscible systems, we have a mechanical means of capturing the oil and returning it back to the compressor. In a refrigeration system, in the evaporator and in the condenser, any oil that enters into this system will be considered to be a contaminant. It will have a negative effect on thermal transfer efficiency. Miscible systems, however, require that the lubricant and the refrigerant be miscible with each other. They have to combine together. A key aspect of this is, first of all, if there is separation, let's say in the evaporator or the condenser, there'll be a separation between the refrigerant and lubricant. And then there is a high possibility that the lubricant will get stuck, especially in the evaporator. So if we have miscibility between the lubricant and the refrigerant, then the viscosity is going to be reduced. We'll see a reduction of viscosity, and that will help the oil to return with the refrigerant throughout the system. Okay? So what controls solubility? So if we have refrigerant lubricant miscibility, solubility is affected by pressure, temperature, the polarity of the gas in the lubricant, and the molecular weight of the gas as well. So this is an important relationship to understand. So this is the pressure and temperature relationship between a refrigerant and a lubricant. So what we find here is that as the pressure increases, the concentration of refrigerant in the lubricant also increases as well too. However, conversely, as the temperature increases, what we find is that the solubility of the lubricant with the refrigerant, or the refrigerant in the lubricant, decreases. And it decreases substantially. So the hotter your operating temperatures, the less refrigerant will solubilize into the oil. And what are the effects of this solubility? So refrigerant has an extreme diluting effect on the oil. And this results in a decrease in viscosity, a substantial decrease in viscosity, and also a decrease in density as well. So we have to worry about if too much refrigerant is solubilized into the oil, that the viscosity will drop below what is required for proper lubrication. And this is an interesting graph right here. What this shows is the viscosity temperature relationship or the solubility temperature relationship. And what we find is that the furthest end of the scale, so at very low temperatures, remember at low temperatures, there's more refrigerant that can, be solubilized into the oil. And that can have such a huge reduction in viscosity, causes such a huge reduction in viscosity that it overrides the normal viscosity temperature relationship. So normally, what we would expect at 10 degrees is that the viscosity of 150 centistoke oil will be somewhere between 650 centistokes. But because there's so much refrigerant solubilizing to the oil, that viscosity can be reduced dramatically. So the end result is there's a couple of ways of controlling the amount of refrigerant that can be absorbed into the oil and also controlling what that final viscosity will be. And we'll go over that in just 1 second. So I also mentioned density as well. So density, of course, will also decrease as the lubricant absorbs more refrigerant. And this, of course, can have an effect on oil collection, but it also has an effect on the thermal transfer properties within the refrigeration system as well. So what do we do as lubricant manufacturers to suggest the right lubricant? Well, first of all, we have to understand what that resulting viscosity will be. So if we understand the pressure and the temperature within the system, we understand the chemistry of the lubricant, and we understand theoretically how much refrigerant can be absorbed into that oil. Again, as the pressure increases, the amount of refrigerant that is absorbed into the oil also increases as well. And at a certain point, the viscosity, of course, is going to drop. And as the viscosity drops, it can drop below the minimum lubrication point. Let's say that's 10 centistokes. So in an ammonia application, at high pressures, an ISO 68 mineral oil may not be the right choice for that application. We may need to go with a higher viscosity oil, or we may need to go with an oil that has a lower absorption tendency with ammonia. With ammonia, however, mineral oils and PAO oils have very low water absorption tendencies, so there's not much more we can do to affect that. What we can do is increase the viscosity of the oil, so your starting off point is higher, and then as the oil reduces in viscosity, at your pressure point, we don't fall below that 10 centistoke level or that minimum viscosity level. Now, we talked before about how mineral oils and ammonia have very low miscibility with each other. So but you can see here that there is some level of miscibility between ammonia and paraffinic mineral oils and even polyalpha olefins. So in some aspects, that's beneficial. So we don't see substantial viscosity decrease, but what we do see is that because some of the ammonia is being absorbed into the oil, there is a reduction in viscosity even at low temperatures. And what this means is that at low temperatures, the oil will become thinner, it will be easier to collect from the refrigeration system, and it will be easier to return back to the compressor as well. So in effect, what we do is through ammonia absorption into the oil, we can reduce the pour point of the oil. This is a chart that shows a PVT curve. So when we're making a recommendation to you, we'll typically provide you with this PVT chart. So it stands for pressure versus temperature. A pretty standard chart, most of you have probably already seen. Fairly easy to use. So if you know your pressure and your temperature, we can estimate the amount of refrigerant, in this case propane, that will be absorbed into the oil. If we know that, we can predict the viscosity of the oil at pressure, under temperature, under live dilution. However, we typically, as manufacturers, do not rely on PVT curves all that much. We have our own calculation tools that can be used to predict the viscosity density, other aspects under a wide variety of operating conditions. And this tool also allows us to select the right oil. So if we find that the pressure, the resulting dilutive viscosity is too low, we can change the formulation. We can look at another product that may have lower absorption tendencies and might have a higher viscosity, and we can select that product that provides sufficient lubrication. So we talked about pressure and temperature. We talked and their influences on solubility, but what causes that affinity? What causes that tendency to be absorbed into the oil? And that is essentially polarity. So as a general rule, in simplest possible terms, like absorbs like. So if we have a gas with high polarity, that will absorb readily with a base oil, with a lubricant that also has high polarity. So for instance, with ammonia is a very polar gas. So what we find is that it is very resistant to absorbing with polyalkylene, it's highly absorb, it will absorb readily with polyalkylene glycols. So that's why in DX systems, you typically see polyalkylene glycols being used in that application. However, at the other end of the scale, with mineral oils and PAOs, these are very nonpolar, so they resist dilution with ammonia. So if we want to avoid miscibility, we go as far away as possible on the polarity differential. If we want to encourage miscibility, we go as close as possible. So you can see here there's multiple polyalkylene glycols, and I think that's important to discuss further. So basically what you find with polyalkylene glycols is that we can control the miscibility with the refrigerant to a significant degree. So if we want to reduce the miscibility of the refrigerant and the lubricant, all we have to do is increase the concentration of ethylene oxide. So you have essentially three general categories of polyalkylene glycols. You have water-insoluble PAGs. These are pure propylene oxide-based PAGs. You have water-soluble PAGs. These are ethylene and propylene oxide mixtures. And then finally, you have pure ethylene oxide, essentially what we call PEGs. So the higher the polarity, higher the concentration of ethylene oxide, the lower the solubility will be, especially with hydrocarbon gases. Remember, like solubilizes with like. If you want to avoid that, the lower solubility with the higher polarity with a lower polarity will resist mixture together. Okay, this is another example showing the differential between the different polyalkylene glycols. You can see that the red line represents water-insoluble, so propylene oxide-based PAGs. The blue line represents water-soluble PAGs, so the ethylene oxide, propylene oxide mixtures. And you can see that there is a substantial reduction in dilution with the refrigerant. So in general, again, if we're working with immiscible systems where we want to avoid solubility between the lubricant and the refrigerant, for ammonia, we choose mineral or PAO oils. But if we want that solubility, we choose a polyalkylene glycol. Again, because the two are very similar in polarity. So again, this reiterates the example of differences in polarity. So again, because PAGs have very similar polarity or have near similar polarity to ammonia, the viscosity dilution, the solubility of the refrigerant in the oil will be significantly higher, and that results in a decrease in viscosity. Mineral oils have very low miscibility, again. So again, that results in a less of a decrease of viscosity, even at higher pressures. Okay. Just to reiterate again, compatibility with the refrigerants, this is also very important as well, because we have to make sure that the refrigerant and the lubricant are compatible with each other. So a big one, of course, is esters and ammonia oils. So esters and ammonia oils are highly incompatible with each other, and they should be avoided at all costs. because essentially what you find is that ammonias and esters will lead to the formation of amides, and these are very difficult to remove from the refrigeration system. With lubricants and other refrigerants, we run compatibility tests to confirm whether or not the oils are compatible with each other, whether or not they're going to lead to degradation of, let's say, metal components, or degradation of the oil, or degradation of the refrigerant itself. We talked a lot about refrigerant-lubricant compatibility and effects on pressure and temperature. But the lubricants, in addition, will also have an effect on the performance of the refrigeration system. This is particularly important in immiscible refrigeration systems, where we want to avoid lubricant entering into the evaporator, because lubricants can act as an insulator in these systems, and that can significantly reduce efficiency. Okay, so just to summarize, the higher the pressure, the higher the solubility, the higher the temperature, the lower the solubility. And then the following slides are just summaries of it. I know that we're a little bit running out of time, but in general, this gives you an idea about the different combinations of solubility versus different types of base oils. So for mineral oils, ammonia has very low solubility, but with highly polar, unpolar gases like butane and propane, you have extreme levels of solubility. For water-soluble PAGs, these EOPO PAGs, we have very low solubility with hydrocarbon gases, but we have very high solubility with ammonia. Okay? And that's pretty much it. If you have any questions, I think we have 1 minute, but anything further, we can always ask outside of the meeting or at our booth at 71111. Okay, thank you. All right, we'll see you at the booth.